So with that, let's move on to the next topic, which are skeleton diagrams. Okay, kinematic or skeleton diagrams. Okay, so we have basically a kinematic or skeleton diagram, also called a stick diagram, is basically what engineers use to draw mechanisms because when they can't draw, right? So the engineers are horrible artists, so instead of having to CAD these or draw these by hand, it's like, hey, let's just do some simplified stick diagrams so everyone knows what we're talking about, but we don't need to be good artists, okay? So, and the reason I'm teaching this is because it's all in the textbook, and anytime you study mechanisms, this is kind of like shorthand for mechanism designers. You might have to analyze drawings and stuff, and you need to know how to read these skeleton diagrams. So that's what the point of this next topic is teach you how to read these, okay? But, okay, look, a definition, it's written on the slide. These are the simplest diagrams that still retain all the kinematic properties of the mechanism. So you can still analyze all the ways it can move, but you don't have to waste time drawing it. And if I teach you this, everyone will be on the same page. Okay, so a couple conventions. Like I said, oftentimes in stick diagrams, they'll make entire links just a single line. That's a very simple way to draw a link. It's just a simple line like you saw on the last slide. But oftentimes that doesn't work because those links might have multiple joints on it, and it actually requires some two-dimensionality instead of just a single line. So when that's the case, to also still be able to draw poorly and to make stick diagrams, sometimes what they'll do is, you can see there's like a wedge there stuck onto another link, labeled 2 by a revolute joint there. What they do is they'll either color in the wedge with hatch lines there, or if they're even too lazy to do that, then what they'll do is draw this little half circle or curve here to say those two lines are the same part of the same link. Okay, so if this little curve wasn't there, then these would be two different links, is how you'd interpret the skeleton diagram. But since they're kind of drawn together with this, or you can see up here in the top right, they can hatch the inside of that as well. So these are just some conventions. Another way you can tell how many links there are is sometimes the book or people will label them with numbers. Here, if there's just two numbers listed for these things, then there's just two links. Right? And another convention just to keep in mind of while I'm thinking of it is usually number 1 is the link that's grounded or held fixed, and 2 is usually the input link. But we'll talk about this later. But anyway, the point is you can know these all have just 2 links because they're numbered just 1 and 2. Okay? But if they weren't numbered, and oftentimes they aren't, you can still know they're 2 links because I just taught you the convention. Okay? Okay, so here's example of 3 links. So if I had a line with a circle, another line, you can know these are 3 independent links that can rotate around this revolute joint. And you can also know there's 3 links there because it's labeled 1, 2, 3. Okay, but a little trick here. What if you need to draw something that's in a line, but it's not 2 links. It's one single continuous rigid bar. That never rotates around this joint, but there's a revolute joint in the middle. Well, the way you deal with that is you draw a square or a half circle here, or you can color it in or hatch it or whatever. But what that is a bridge that represents that these 2 seeming independent links are really just one and the same link. So you bridge them together. So now you can see here, even though this looks almost identical to this, because of this bridge here, there's 2 links, and we label this one. You can see it's the same number. They often won't be that kind, but they'll expect you to interpret that. So that's 2 links instead of 1. Okay, so of course engineers don't want to draw gears because they have a lot of teeth and they're actually quite complicated to draw, the involute profiles of the teeth. So to simplify them for skeleton diagrams, they just draw circles like this. Okay, and if it's an external gear, you'll draw this. Sometimes they draw the arrows in the direction to show how they're moving. And these are internal gears, and you can see they draw an arrow there. Okay, but that's pretty clear. So if you see circles in this class, they are gears. Okay, so pin joints, pin and slot joint. Okay, here's we've kind of looked at this. The green thing here is the link, and it's got a pin coming out of it that's fixed to it, and then behind it you have this other link with a slot in it. And remember, for two-dimensional planar mechanisms, that has 2 degrees of freedom, the translation of the slot and rotation. And it's a higher pair, remember, because it's just it's touching just at 2 lines, and you assume they're not pressed against each other, because then it would be touching a surface. But pin joints are regarded as higher pairs. Okay, but that's not the point. The point is, here is one way you can draw a skeleton diagram to represent this. Okay, so here they actually took the time to draw the bar for link 2, and they do a circle for the pin, but then they were super lazy for link 1 and just drew a line with like kind of a slot on it. So it's a really weird way to do it, but when you see that, that means a pin and slot. Okay, you can imagine one would move with those 2 degrees of freedom. Okay, so slider joints are actually really confusing, especially when you think about how you show in a or prism joints or slider joints, right? When you compare it with how things are drawn in skeleton diagrams for fixed or grounded bodies. Okay, so I'll show you here all these examples. Everything above here is a slider prism joint where you could draw it in a skeleton diagram. The top, they actually took the time to draw the 2 different links and label them, so that one's actually clear. That means they slide kind of transverse with each other. Okay, this is a little lazier way to do it, just a straight line with a box on top. That means, again, it's a slider prism joint, and that you can think of that box sliding on top of that other link. That's 2 links, and nothing's particularly grounded in any of these. If it's a spatial 3-dimensional mechanism, they might have a box on a line but put an X in it, meaning it can only slide along that line, but it's a spatial mechanism, so it may not stay on the plane. You'll never really confront those in this class because they're sticking to planar mechanisms, but it's something to be aware of. More common is just the line goes right through it, so you can think of a box on the line sliding along its line, kind of like this. You can see here, this is a link that slides on the white link. The black one slides on the white one. This is a gym machine, a slider prism joint here. You can kind of see where this came from. And then another thing, if you have a box on a line with hatches there, that means this bottom link is ground, but the box can slide on top of it. Okay? So now here's where it gets really confusing, because if it's just a box without a line with hatch things on it directly, that means that box is a grounded, held, fixed thing, and it's not a joint. It's just a link that's grounded. Okay? So really the difference between this and this is you extend the lines and put the hash lines outside of it. Okay? And that's how you differentiate there. The other confusing thing is if they ever round this box's top corners, like a circle or something, then even though this looks almost the same as this, and you think, well, this guy slides on it, just because they rounded it, this is grounded and held fixed. It's not a slider joint or a prism joint. And another trick is if they just did this and did this kind of thing, you might think it slides, but nope, it's not. This is also fixed, and this is also fixed. Okay, so be very careful to look for the rounded top corner. That usually means it's not a prism or sliding joint, that it's directly held fixed by these hatch lines. Okay, so yeah. Anyway, it's a little confusing, and honestly, not all the conventions hold true. So sometimes you just have to ask your teacher what it is, or the engineer, or use your common sense and say, would anyone design a mechanism that is just grounded there, or should it be sliding? And then do your best guess. But this is the most confusing thing in skeleton diagrams. Okay, kinds of links. Okay, and with this we're almost done with the first little video installment here. Okay, so you name links, the rigid bodies, according to how many joints are on it. Okay, and it's just the number of joints. Okay, so a binary link is a link with, not surprising, 2 joints. That's bi means 2, right? So in this case, we have this, I guess it's not a mechanism because it's not a closed thing, but we have 3 links, and these 2 are joined together by this revolute joint, those 2 are joined together by that revolute joint. But this one in the middle here, it has 2 joints on it, 2 revolute joints. It doesn't matter how many degrees of freedom they have. It doesn't matter whether it's low or higher order pair. None of that matters. Just it has 2 joints on it, so it's a binary link. Okay, so here's other examples of binary links. This is a box that slides on this other link. This line here is a link, and that box slides on it with a prism joint. And then on the box, there's a revolute joint that links to another link that can rotate. Okay, so if you're just looking at this box link, how many joints does it have on it? It has a prism, a sliding joint, and it has a revolute joint. That's 2 joints. That's a binary link. It has nothing to do with the degrees of freedom. It has nothing to do with lower or higher pairs, anything. It's just how many joints on it. This is another one that's, again, a link here and a box, another link that's sliding on it. But here's another skeleton diagram trick. Instead of drawing the box actually all the way down here to to have the revolute joint on it, they just draw this little piece down here. But just imagine this is all totally rigid and locked up, and they were just lazy, and the revolute joint was down far, and then that's another link coming off of it. So this one has 2 joints on it: the sliding prism joint and the revolute rotational joint as well. So they're all binary links. Okay, another kind of link is a ternary link. Okay, and a ternary link, not surprising, is a link with 3 joints on it. Okay, so here, this is the clearest one in the top left. You see a link, and there's 3 circles on it for 3 revolute joints. That's got 3, so it's a ternary link. Okay, the one in the middle there, you might think, if you just saw it drawn like that without those curves, like this curve up here and the other 3 curves, then like you see on the far right, then that would not be a ternary link because there's 3 links in there, and they're each binary links, right? But once you connect them with this little curve, that says they're one and the same link. So because that triangle, those 3 lines in that triangle in the middle have those curves, they're essentially one and the same link, and you'll note there's 3 circles on the corners, and those 3 circles are 3 joints, and so it's a ternary link. Now, like I just said, the one on the far right is not a ternary link. Which is a little confusing because of this slide. It is not classified as a ternary link. It's actually 3 binary links connected together like a truss. Okay, but the reason it's like on the same line and these like lines show that it's like equivalent is because it moves the same way. Okay, it behaves as if it's a ternary link. Okay, and basically has 0 degrees of freedom. So if you look at this one, just going back to our definition, if I asked you, is this a mechanism? You'd say, well, okay, does it consist of multiple links connected together? Yes, there's 3 of them, 1, 2, 3. And okay, are they connected together by joints? Yes, they are. Here's 3 revolute joints. Okay, and is one of them held fixed? Well, sure, I could hold. Number 1 is usually the ground; it's held fixed. Okay. Is it a closed kinematic chain? Yes, it is. It's a closed, nice chain. But then the final one, does it move? No, it doesn't. It's a structure. It's static. So it's not a mechanism. It's a static structure, which is why it behaves as one single link, because it has 0 degrees of freedom. It would behave exactly the same as these other 2, which is why you see the equivalent sign. But just so you know, only these 2 would be classified as ternary links because, right, the other one is 3 binary links combined together. Okay, here's another example of a ternary link. We're pointing to this link below here, so ignore all this. The prism sliding joint between this line and the box is 1 joint, and then you see 2 circles on its 2 ends. That's 2 other revolute joints, and so that's 3 total joints. That's a ternary link. Okay, this one, remember with a bridge, that basically, you might think, oh, look, there's 2 binary links connected together, a revolute joint, but you say, no, because of the bridge, this is one and the same rigid body that's all connected together, and you can see there's 3 joints on it. 1, 2, 3 revolute joints, so it's a ternary link. Okay, here's other examples of ternary links in skeleton diagrams. This is really bizarre how this is drawn, but people draw it like this. So, this big, all these boxes and these half circles, that's all one link, and they slide on this link that goes all the way through it. They slide on this link that goes through it, and then there's a revolute joint. So that like cross here is a ternary link because it has 3 joints. It has 2 prism joints and a revolute joint. Okay, so that's a ternary link. Okay. Now this guy here, this circle here, which this says it's pure rolling, right? So it might be a gear or something. Is connected to this grounded point. It's ground because of the hatching there, and then 2 other links there. Okay, by revolute joints. Okay. So you ask yourself, how many, first of all, whether this said rolling or not, it doesn't matter. If it didn't say rolling, then you'd assume it can roll and slide. That means you could imagine this just shearing along like, when you drive your car, the wheels are rolling, but when you slam on the brakes, if your car keeps moving forward, the wheels are sliding. So if this is not constrained to just roll, then it could roll and slide. So it's 2 degrees of freedom down there. But again, what makes something a ternary link has nothing to do with the degrees of freedom. Because if you added degrees of freedom, it's like there's a rotation here, rotation, and possibly sliding. So 4 degrees of freedom, right? But here, if they say rolling, then it's only rolling. It'd be 3 degrees of freedom. But like I said, doesn't matter degrees of freedom. You got to ask yourself, how many joints are on this? Well, there's 1 joint here, and just 1 joint there, whether it's 2 degrees of freedom or not. And so since there's 3 joints, it's a ternary link. Okay, so quaternary link. Okay, obviously that's a link with 4 joints on it. You can see there's 4 revolute joints on there. Okay, and again, if you go to the one in the middle, you might be tempted to think there's 4 different links, but there's not, because these curved surfaces, or these little curves inside, saying they're all one and the same link, and therefore, since it's one and the same link and it's got 4 joints on it, it is a quaternary link. Okay. But now, if you leave out these curves, okay, then you have to assume that there are 4 different binary links. Each one has 2 joints connected to it, or on it, right? Revolute joints in this case. And this is not the same. So not only is it not a quaternary link because it's 4 binary links, but it also doesn't move the same. Okay, this is a true mechanism and actually a linkage, because it consists of rigid bodies. They're connected by movable joints. There's a ground, okay, that's held fixed, which is 1, and it's a closed kinetic chain, and it can certainly move. Think of a 4-bar, can move back and forth. So it definitely has, a degree of freedom, and so whereas these ones don't. Okay, so anyway, just in contrast to the last ternary example. So you're understanding these definitions. And of course, it's a linkage, this one on the right, because it has lower pairs, and it's a mechanism. Okay, so now we go to other examples here. Okay, this is not a quaternary link, okay, because it consists of 3, okay, links. Okay, this link would be a binary link, this link would be a binary link, and this link, remember, it's bridged together, would be a ternary link, 1, 2, 3. Okay, so you would not classify this as a quaternary link. And you would not classify it as a ternary link. You would classify it as 1 ternary link and 2 binary links. Okay, and that's because there's 3 joints on this ternary link and 2 joints on this one binary link, and 2 joints on that binary link. Okay, the reason there's this equal sign is because this would have no degrees of freedom. It would act as if it's a rigid link with 4 points on it, and so this would be kinematically equivalent to a quaternary link. Okay, and same with this. The only difference between this and this is that we gave this an angle. So you see, you can bridge things that aren't straight if you need to draw an angle there. But if there's a square or a circle or a bridge thing or hatched-in thing, that means this is one and the same thing. And notice these are both labeled 1, which means they're the same link and they're ground. Okay, so this would not classify as a quaternary link, just like this, and this don't, but it would behave like a quaternary link because it would all be locked up with no way to move, and it would have 4 joints on it. Okay, but again, on an exam, if I asked you, is this a quaternary link, you'd say no. It is 2 binary links and 1 ternary link that behaves together like a quaternary link. Okay, so the difference between analysis and synthesis, and then we'll be done with this first little video here. Okay, analysis, and there's a lot of words on the slide, but it's actually a really easy slide. Analysis is, I give you a mechanism. You know what the system is. Say it's a 4-bar, say it's a slider crank mechanism, whatever it is. I give you that mechanism. You can measure it. You know its lengths. You know everything about it. But then I tell you, for an input, if I move the input link 20 degrees, say, what's the position of all the other links? Okay, so you know the input. It's given. That's the 20 degrees thing. And you know the system The question is, can you calculate the output, which is maybe the follower link, what angle is it at? Okay, how does it move? Or what speed is it going in? And these kind of things. That's analysis, okay? And that's what we're going to largely spend our time doing in this course, okay? Now, design is a little more interesting, but much more complex, where you know the input and you know the output, but you don't know the system. You have to design it. So say it's like, well, I want, I have a black box, and I don't know what's in it, but I want some input link to move, and when it's 20 degrees, I want the output link to be 30 degrees. And with these different speeds or these different accelerations or whatever, you know the input and output, and then you say, go design it. That's what people will likely do with consulting. They'll want you to design a mechanism that does what they want, okay? All right, so with that, that wraps up this first video, and we'll continue on with the next video.